class should also be holiday. So maybe I will change this to Zoom as well. So, so this one is Zoom. So after this lesson, I think in here I can still be here, but I will be in here for Zoom only. So, okay. So this one is Zoom. So if you want consultation, I will be here. Okay. So this one is Zoom. And so after this lesson, I will be seeing you at the end of February. Okay. Okay, so let me just repeat once more. So after next week, the week after next week is Zoom.
好慢晒喎，呢個分和40，咁即係1個月時嘅，要分咗40，45個鐘度，45多加得勁，但係最後都係唔夠。呢個就20分咗，就差手機。
老師，我們可不可以2月14號上線上課，然後在下一周那一周就不上課，就勸你一下，因為初5的那天要打麻將。我在你先描述你們啊，我是太細好了，可以，就是上線上課可以。
但不影響。
So I think 24號打麻將應該不在我的課。
21。
不是，就是2月14號這一天就是 Solution 或者是線上的 Zoom 上課，然後2月21號的那一周就不上課。
哦。
可以吧？
就是這個是 Zoom，然後這個是。
就是把它勸解一下，對。
哦，所以是這個就是 Zoom。
然後下面那個就過年，對。
哦，這個就放假。
對，這樣可以啊。你們可以嗎？
沒有意見。
因為我們14號
你有約是嗎？
就是有東西要做。Okay, so I will be seeing you on the
星期都期待要做嘅。
印度嘛，
Okay, so so today we will be talking about the latest architecture of image vision language models, which is a fully transformer model. So these kind of models use only transformer. So when you see it is this part is the encoder and this part is the decoder. So from here, this text is something like license of McDonald's, and the objective of this model is to essentially translate all these patches or these image patches to these text. So I will just ask a very simple question. When the model generates the L, what kind of information does it need from these kind of patches? Okay, a very simple question. If I want the model to generate this L, what kind of which part of the image do I need? So I will need this one and this one, right, to generate this L. Okay, So in here it says multi-head attention, and this one says masked multi-head attention. Because this part we do not mask, so all these patches can attend to this single L. That's why it can sort of pick a part of image in here and pick a part of image in here and recognize, oh, there is an L in here. Okay. So Microsoft replaced the convolution neural network with the vision encoding transformer. So this part is not done by CNN anymore. This part is done by the transformer model. And replace RNN with the transformer decoder. So the decoding of the text is performed also by transformer. And it reached a very good result in the evaluation. And it is the state-of-the-art benchmark in 2021. So it pre-trained millions of images, and it also, in stage 2, it also used handwritten images and also scenes, and it's fine-tuned also using handwritten handwriting and also receipts. So almost dominating all tasks in handwriting, receipts, and consistent improvement up to 40 to 50% of benchmarks. So it is very similar to what we have talked about. So the image is split into multiple patches, and from those patches we project all the image into embeddings like before. And then with the embeddings and positional encoding, we have the final encoding of the image. Okay, so and then with this encoded image, we project each of them to the questions, keys, and value, like 2KB, like what we have talked about. It is a multi-headed transformer. So if you want to implement this in PyTorch, okay, so after projection, you have to apply the attention score, so you softmax and force it into a probabilistic matrix. And then the final part is you project the head concatenate back into the output. So these are the details of the vision transform. So the encoding part, so all we have talked about is the encoding part, and we have to encode this using the decoder. So the first token that we use for the decoder is always the beginning of sentence token. So you add the beginning of sentence token to the decoder, and then start decoding. And then the decoding mechanism, as we have talked about, is using the causal mask. So zero out the top part of the matrix and allow only the bottom part of the matrix. So again, we are doing autoregressive here. So this is the overall structure of the transformer architecture. Doing the OCR, focus on the OCR. So it kind of break all these into image patches, feed into the multi-headed self-attention, and then for the encoder part, all image parts see all other image parts and project into a source of encoding. With this encoding, we do the multi-head cross attention when decoded back into different heads. But just last month, the pedal OCR released it, so this year, and with a very small number of parameters, but still larger than the previous one. The amount of parameters is around nearly 1 billion parameters, but it's still very small compared to current computational power. And it is layout aware, so it can detect polygons. And it's also multilingual, so it extended the language support. And also, it can recognize seal and text. So when you have a stamp, when you chopped it in the document, in some official documents, it can recognize the seal, so it can directly recognize the company name from the seal, and also it can handle scenarios like skewed, scanned, grab, photo, and light. So the performance is actually the current best. It surprisingly beats the OCR performance of Claude 3.5 and Gemini 3 Pro because it is so lately released. It just released it, I think, 2 weeks ago, I think a week ago. So I have not been able to test whether this is the claim, but I think if they claim this to be that accurate, it is quite massive, like even better than Gemini 3 Pro with only 1 billion parameters on the OCR task. Of course, in other tasks, it's not beating the Gemini Pro. So you can have a look into this model. It is released, so it compares all other models. If you view into their website, they claim for the OCR task, they claim they have beaten all Google models as well as DeepSeek, I think somewhere on the OCR task. So it's quite a bold claim, but we can all download this model and test it in our HPC server. So this is their official website, Pedal OCR, which is slow. So they just released this one using different scanned documents. So let's go back to the slides. Okay, so if you are interested, you can work on this project and try to fine-tune this model. If you follow the lab, you will find you can have some slightly gain performance for a very short fine-tune. So you can fine-tune it and quickly publish a paper, say, oh, I've beaten this model, but it has to be significantly better. So this is their paper, and they said they used document parsing, they have layout analysis, and also have positional categories, and feed into the language model. Actually, they have already, this is not new, this model. and the vision encoder and outputting all text. So compare with the traditional one, the Microsoft one, it is built based on their own decoder model, but they also used, they actually used a convolutional neural network in one step, but mainly they focused on visual transforming. And this supports multilingual and rare scripts, full page polygons. It has text spotting capabilities and suit recognitions. The license for this one is Apache 2. So Apache 2 also allows commercial use, but for the details, you have to check very carefully. For this one, the license is MIT license. So the layout, they can understand the document structure. So traditional OCR, they have only say invoice something, total something, just words but no context. In the layout aware OCR, you can directly output a JSON structure which indicates, so this is the invoice ID and it captures the invoice ID. So I've mentioned it can auto-detect the ID, date, total, and line items. For medical records, it can detect digital handwriting notes, integrate with the EHR system, and also enable to search and retrieval. So these are the modern OCR applications. I would claim, I think if you are very good at OCR, I would say that it requires minimal review needed, but I think for medical and legal cases, I think it's still important to manually review the OCR because the risk is too high. And for receipt, so in here, we will try to aim for 2 to 5% accuracy. So for invoice and receipts. So for this model, because it's quite small, you can train it in our HPC server. So last time we talked about the, there are 3 ways to tokenize the image. We talked, for the first semester, CNN, you can convert the image patches, the old image into CNN features, and last lesson we talked about how to convert the image into visual transformer patches, and there is a last one. So it's called the visual EQ variational autoencoder code. So essentially, it is good for generating images. Here I just put up some slides for you to reference to for the VQ-VAD. So in your project, you can try all these encoding methods and try to swap around or play around with the receipts to try if you can outperform the latest state of the art. Okay. If you can't outperform the model, it's still okay. You just have to state why it cannot outperform the state of the art model. Okay, so before we talked about variational autoencoder, just a quick review on what is an autoencoder. It is Is it a supervised, unsupervised, or reinforcement learning? So have you learned about the autoencoder in the last semester? No. Oh, 没有. Okay. So this is a basic autoencoder structure. It is actually pretty simple. If you have an input with more dimension and you want to squeeze it into a lower dimension vector, you can train it by putting, say, an image in here and an image in here, and you just train the neural network and you will get the latency vector in here, and you can treat this as some kind of code encoding the X input. Actually, can you give me one very simple autoencoder example that you have learned in the last semester? So a very simple autoencoder, you can use CNN to do it. Because CNN tries to reduce the image into a smaller dimension vector, and then from the smaller dimension vector, it can actually kind of increase up dimension into the original image. So the encoder and decoder is not the important part here. The important part is the dimension of the latent vector in the middle. Okay, so this is what an autoencoder does, is try to compress the input C into some kind of representation. And for the decoder, it will decode back the latent representation back into the original image. And the goal is try to minimize the reconstruction error. Okay. So this is what the encoder is for, and now we are switching to variational autoencoder. So instead of forcing, the idea is the same. The idea is still we are trying to minimize the reconstruction error using a smaller latent representation of C. So, but we are doing it in a different manner. We will do it, we will forcing the C representation into some sort of distribution that we can sample from. Okay, so in this diagram, when we pass through the encoder, we will force them into two different vectors. The first vector represents the mean of some sort of distribution in the latent space. And another vector, we will force it into some sort of standard deviation of a sample space. And then we will try to use the decoder to decode from this latent space back to the original original image. Okay. So here I will make very clear. I'll make an example of why we need to do this. Okay, so in here, we are forcing the encoder to encode our image into some sort of mean and with some sort of standard deviation. So when you encode your image, you will generate some points in the latent space. Assuming your latent space is a two-dimension vector, you can visualize with these sorts of diagrams. So these plane diagrams. So each point in here represents an image. So when you feed an image into your encoder, it will actually end up in a 2D space. Say C1 is the first dimension of the latent space, and C2 is the second dimension of the latent space. So by doing this repeatedly, you will have some sort of sample. So this is an example of the variance of equals to 1. If you, of course, increase the variance, the dot will be much more scattered. And if you reduce the variance, the dot will be also more scattered. And using this dot, you will use a decoder to decode this point back into the original image. So I want to ask one question before moving on. Why do we, or what do you think, or why do you think we want to use this kind of mechanism instead of the original decoder? Why do we want a variation? So the variational terms in here refers to this variation, this variance, okay? This variation refers to this variance. And then the term autoencode refers to encoding a high dimensional data, such as an image, to a smaller dimension, such as Z. Z in here only have 2 dimensions, okay? Why do we want to do this for images? You can think of C as some sort of okay, so let's have some AI, let's see some AI generated image. Okay, so what are the patterns of AI generated image in contrast to a real photo? So maybe I will use photo to be a more precise term. This one is good. Okay. So for AI generated photos, you have some sort of different features, right? With this photo, you can generate a photo with, say, some grass behind, or for some photos, you might have some space, a background of some cyberspace background. Using this method, you can actually control what you generate, because, say, you have another distribution in here. You can actually blend, if you encode this space, say, if you keep feeding cat images in here, all of this pattern will be generating a cat, right? If you generate in another batch, if you try to encode, say, bananas in here, you can efficiently decode different image like bananas. So if you want to generate something in between, like a cat-like banana, you after this sampling, you can effectively sample from the middle. You will get something like a cat-like banana image. That's why the variational autoencoder is introduced, because you can actually, from this latent space, generate some high order concepts. So, but this sort of generator mechanism have its problem, but effectively solved by some clever researcher using the reparameterization trait, but you do not need to worry about this. So the main point I want to stress from the slides is that using the variational autoencoder, you can blend different style or different images or different concepts using these sorts of latent space. Okay. So the BQ variational encoder take one more steps. So the step that it took is forcing the latent space back into the discrete space. You can read about this at home, but I want to just go to this slide. So this is the main feature that I want you to take away. So for the vision transformer, it is continuous, and for the BQ variational autoencoder is discrete. So what the BQ does is essentially from the continuous space in here, it actually use a cookbook to discrete the to make the continuous latent space more discrete. So these are good for generation purposes, and visual transformer are good for understanding. So if you think about in your project, if you want to do something new and you want to say generate different images, you do not want to use vision transform, although you have a good understanding of what the image is. But for image generation, you want to use a different mechanism to generate images. So this is the takeaway. So do not confuse between, oh, if I can ask what is in the image, I must be able to generate using the reverse mechanism. No, this is not the case. You have to use a different model structure. Okay. Okay, so for your project, you can do either image generation or image OCR classification. Okay. So now we are going to talk about the basic architecture of the latest model. So for the lab, if you run the lab, you will see you have this kind of received, and you will generate text something related to something in the format of this one. And for handwritten notes, if you run the lab again, the code is in the Moodle. So if you run code example 02, you will generate all this text like receipt. It also works for English and Chinese, and it supports, I think, 111 languages for this model. So the Baidu OCR model is kind of like, it's the same idea using the encoder and decoder. So we have talked about encoding, and it used a dynamic resolutions up to 28 times 28 times 2048. And it will output the visual embeddings. Handles the very document size, and also for the native resolution patches, so you can directly feed the whole image into this model. For the decoder, it will do a auto-regressive generation from the embeddings. Of course, using the cross attention we've talked about to the visual encoders. So this is the basic architecture of this model. We have, on one side, you input the image document, and the other side, you ask the question. So from the document, you feed through an encoder, which is it uses a convolution neural network in the patch embedding. So it's kind of a mixed model. It do not only use transformer only, but this side is only for the embedding part. And it uses a very special in here, it's just use positional embedding for the encoder. So, and then it passes through the visual transformer that we have talked about. 27 layers. So, with layer normalization and multi-head attention and layer normalization and and just simple neural networks with obvious with some simple activation. So after the vision transformer, it projects into a vision language projector. So instead of feeding all the embeddings into the language model to generate text, it will feed all the embeddings to the vision language projector. So the image, after all these projections, and alongside with the text token, it will feed into the decoder model, the language decoder model. And the decoder stack use three, I would say, kind of new technology, which is group attention, group query attention, 3D positional encoding, and also multi-layer perception. So it's just a simple neural network. Okay, so I will talk about something new that they used in this model. Instead of lining up the image all together, they kind of put the beginning of text, beginning of sentence text token, a text token that you design yourself, and then embed the image within the text, within the POS and the actual text token, and swap the image embedding inside. So that is how they kind of merging the two, the image embedding as well as the text embedding. So this is the final matrix of feeding into the decoder model. So group query attention. The idea is to save some space. So instead of having 16K and 16V, it use only 4KB heads shared across a group of cube heads. So the questions, so this is kind of saving mechanism that is used. And that's why I think the number of weights is so small because of this group query attention, and it's also faster. So the main idea is not to compute all the 16K. It just repeated 4 times using the PyTorch broadcast function. So rotational, positional encoding. This is actually, I think, I won't say new, but I think this part actually handles the skewness of the text. In language models, words appear in sequence, but it kind of in here you have some image to deal with. So okay. Okay, so maybe you can read those after class, or I can sort of bring up your memory from last semester. Anyone recall the position, how we can make the positional encoding from the last semester? Okay. So positional encoding, right? So recall this slide, positional encoding from the last semester. Recall this one. This one, right? Remember this one? So, so this is the very basics of the transformer model. You using sign to kind of make the positional encoding for each text. Because you know the cross attention mechanism cannot identify the word order. They have to use these kind of encodings to encode each part in order to identify the order of text using sine and cosine mechanism. In here, okay, in here, it still uses the same kind of idea, but it kind of use different mechanism to put all these rotational sine cosine frequency into the encoding. So at the end, it still use this kind of frequency to encode the position of each token. So after the decoding model, it will output and generate the text. So the key features, to summarize, there are two parts. The first part is the encoder part. So the encoder part only takes up 0.6 billion parameters. It preserves the document's aspect ratio. And the decoder part, which is optimized for multi-model tasks, cross attention to the visual encoder. So this is quite effective in multilingual generations. So it can handle SKU documents, wrap the pages, scan the PDF and various lighting, and so on. And it is kind of the current best, as I've mentioned. It supports up to 111 languages. Also Asian scripts, including Chinese, Japanese, Koreans, and so on. So, and it also handles mathematical symbols, Arabic, and some technical notations. Okay, so it also kind of layout awareness, as I mentioned before. The pre-trained data set is around 46 million image to text pairs, and include all font size and scripts. And it's also specialized training on the post-training part, which is around 5.6 million post-training data. So in their website, they stress that they have the sealed recognition samples, which is their major claim of advance, including complex layout as well. Okay, so the task in here today is to fine-tune this model. So these are the official training details for we're using the optimizer called add-on. If you record the optimizer from last semester, you'll be using, I think I won't say current best, but one of the best optimizer is add-on. So the algorithm for gradient descent, one of the algorithms for effective gradient descent, and the post-training samples, we will not be using that much samples during the fine-tuning. So full model fine-tuning, we will be not using full model fine-tuning, we will be using LoRa. Okay. And these are the deployment options. I think because this model is small enough for you to run it on your own PC. But I think if you have a sufficiently large GPU, you can fine-tune it without the HPC server. Okay. So these are the project. If you are working on these kind of project, you might find this model useful. So you can, when you are working in your project, you can refer to these slides. Okay. Okay. So in the training subset, I've picked 5,000 samples. If you want to increase the sample in your project, you have to tell me, and I have to download it for you. Because in the server, I've already downloaded 5,000 examples in the server for each of you. And because you are all sharing the same set of samples, if you want to increase this, you need to tell me, and I will increase the data set for you. so we will be trying to fine tune it with a data set which is not as big, but we will be getting a subset of data from this OCR data set. Okay, so if you are interested, you can go and have a look. So these are some characteristics of the actual data set that we'll be using in the fine-tuning. Mostly English. While the latest model supports 111 languages, training subset is mostly English dominant. So these are what will be in the lab. And of course we will be splitting the data set into training and testing data set. Okay. During your project, you can choose to do the data augmentation. The techniques is trying to rotate the original image to some sort of degree, change its brightness, contrast, or maybe add some noise. And the benefits of data augmentation, as you have learned in the last semester, is better generalizations. And of course, in the real case, there may be more noise than you might think. Okay, so the first part of the lab, you should kind of have a better understanding of what the examples look like. So so the code is already uploaded into the Moodle. You can download the code from so the code is in here. You can download the code in here. And if you upload to the HPC server, it should be in the code examples. So the first code is to load the OCR data set and give you a better understanding of what is in the data set. And the second one is try to do some inferences. So after some inference, you should see what the output is. And the third one is for you to fine-tune the the latest model. And the fourth one is for reporting. So in the project, I expect all four of the stage to be reported. The important part of this is to evaluate what's the fine-tuning results. Okay, so here is the what the output looks like. It will load the 5,000 OCR examples from Hugging Face. It is not actually loading from Hugging Face because it's already in the server. And then the sample one will be something like in this language, I think it's French, and ask about what is in the language. And the inference part, you should see the inference from the log. So essentially, it is kind of extracting an image and put the text back into the output of the code. And for the fine-tuning part, I've done so many fine-tunings. Okay, for the fine-tuning part, it used only I think 100 examples for the demo, but in the project, please change it back to 1,000 examples. So let's view the actual code, the actual image. So after running script 1, you should see examples like this. These are the data sets. The loading example code is similar to the last 3 lessons. So essentially, it's loading the data set from Hugging Face. If you want to directly view what's in the data set, you can go to this website, and there is a button on the top right. It's called Data Studio. Okay. So if you click into this link, so if you click into this link, the actual data set that is pulling from is this one. You can click Data Studio and kind of find all the images, tag questions, and answer for the data set. For the Okay, so the fine-tuning plan, I only use 100 steps for demo training. So these are the code. You should be able to kind of read what's in the code. So the first step is to load the model, and we are fine-tuning it using LoRa. So remember the R, and in the project, I want you to try different parameters. Say, try to change the R into say 8, 16, and 32. For the LoRa alpha, you can also change this parameter. So we will inject the LoRa adapters into the model, and using this training argument. So 100 steps around, I think 10 minutes. Okay, these are some kind of parameters you want to play around with. Remember last time we used a much smaller learning rate. For this model, I think the learning rate is okay if you stick to the learning rate from the code. Paged Atom 8-bit, you can read this at home. Form of steps, save steps. Okay, you can read these at home. Code examples. Okay, so before you go, actually, I want you to know that if you run the code correctly, you should be able to find an improvement. So you should be able to find around a very small improvement on different metrics. Okay, so I've only run this for I think 100 examples in your code. Please try to scale this up and see if you can achieve more improvement. So after the improvement, I think you can publish a paper because I think this is the latest. I think this is the latest model that you can get. So after training this, if you find an improvement, if you find an improvement during the evaluations, please feel free to publish a paper or something like this. And in the error analysis, I think the top worst cases is actually very bad. So reach up to I think 64% for the first cases. Okay. Okay, so thank you and wish you have a happy time. So I will be seeing you at, I think, not next week and also not the week after next week. So I will be face-to-face seeing you by the end of February.
我给你点儿，别